Have you ever wondered why giant ships made of metal don't sink? A piece of steel thrown into the water will sink straight to the bottom, but a vessel weighing hundreds of thousands of tons will cross entire oceans without disappearing. This doesn't happen by luck, nor by engineering magic. There's a very clear reason behind this, and when you understand that, it completely changes the way you look at a ship at sea. A piece of steel thrown into the water sinks without question. This happens because steel is denser than water. Now take that same material, multiply it by thousands of tons, mold it into the shape of a ship, and put it in the ocean. Not only does it not sink, but it crosses continents carrying containers, cars, grain, and fuel. The contrast is real. The material is the same, but the result is completely different. So the real question isn't why steel sinks, but rather what changes when it becomes a ship. The answer begins by dismantling a common idea. The ship doesn't float because it's big, nor because the weight is evenly distributed. It is not simply resting on the surface of the water either. What happens there is a very specific physical balance. The hull enters the water until it reaches a point where the downward pulling force and the upward pushing force become equal. From then on, it remains stable at that level. There's no magic, no hidden trick. There is a clear rule of physics at work all the time, and that's what we're going to break down now. When someone tries to explain why a ship doesn't sink, the answer usually comes up as one of these. Is it because it's big, or is it because it has air inside? These explanations seem logical, but they don't get to the root of the problem. Being big doesn't make anything float. If size mattered, a huge sheet of steel would float, and that's not what happens. And the air inside does help, yes, but it is not the principle that sustains the ship. It is the result of a project that seeks something more important. The key point is that buoyancy doesn't depend solely on weight. It depends on the relationship between weight and volume. What really matters is how much water the object displaces when it enters the sea. If the displaced water weighs the same as the ship, the buoyant force balances the weight and it stops sinking. It moves less, it continues to descend. So the secret isn't in the size alone, nor in the material alone. It's a combination of total mass and space occupied. This is what begins to completely change the way we look at the problem. To fully understand what's happening, we need to talk about a rule discovered over 2,000 years ago, Archimedes' principle. He says something very direct. Every body immersed in a liquid experiences an upward force equal to the weight of the liquid it displaces. It's not an opinion, it's not a loose theory, it's a tested, measured, and applied physical law in naval engineering to this day. This means that when a ship enters the water, it begins to push water out, and the deeper it sinks, the more water it displaces. There comes a point when the weight of the displaced water is exactly equal to the total weight of the ship. At this point, the forces balance out. The ship's weight pulls it down, the buoyancy of the water pushes it up, and it stops sinking. That's where it floats, not because it's light, but because it has achieved equilibrium. And this thrust doesn't appear out of nowhere. It exists because water pressure increases with depth. The underside of the hull receives more pressure than the top side, and this difference creates a net upward force. It's simple, but powerful. Now comes the part that really changes the game. What determines whether something sinks or floats is the average density of the whole, not the individual material. Steel alone is denser than water and slingshot, but a ship is not a solid block of steel. It is a hollow structure filled with internal spaces. When you consider the total weight divided by the total volume it occupies, the average density of the ship can become less than that of water, and this is what allows it to float. Think about the difference between a solid steel ball and a huge hull full of compartments. The ball takes up little space for a lot of weight, so it displaces water before sinking. The ship occupies an enormous volume, so it displaces a much larger amount of water. If the displaced water weighs the same as the ship, the buoyant force balances everything out. The material is the same, but the result is different because the format completely changes the relationship between mass and volume. That's where engineering comes in. But floating is one thing, being stable is something completely different. An object can float and still flip over easily. In the case of ships, an essential concept of naval engineering comes into play: stability. Here, three important points emerge: the center of gravity, where the total weight is concentrated; the center of buoyancy, where the force of the water acts; and the metacenter, which is a reference used to measure whether the ship tends to right itself or capsize when it tilts. When a ship tilts to one side due to a wave, the shape of the hull causes the center of buoyancy to shift. This displacement creates a return momentum, a force that attempts to bring the ship back to its original position. For this to work, the center of gravity needs to be well positioned in relation to the metacenter. If the center of gravity rises too high, the stabilizing effect decreases. That's why that poorly distributed load can be dangerous. Stability is not luck, it is calculated with precision. And that helps explain why a ship doesn't capsize with just any wave, but also why it can fall over if something goes wrong. The first risk is water entering where there should be air. When internal compartments fill with water, the average density of the ship increases. Furthermore, this water can move internally, altering the center of gravity. If it rises too much, the return momentum decreases and stability is compromised. Another critical factor is load distribution. Containers stacked too high or poorly balanced raise the center of gravity. If the metacenter is no longer above the center of gravity, the ship loses its natural tendency to right itself. From that point on, any inclination can increase instead of being corrected. It's not the metal that makes the ship sink. It's the loss of balance between weight, buoyancy, and stability. When this relationship breaks down, the entire system ceases to function. Therefore, none of this is left to chance. Before a ship leaves the shipyard, every detail is calculated. Maximum displacement, center of gravity position, metacentric height, load capacity. Engineers use mathematical models and real-world tests to ensure the ship remains stable, even in difficult conditions. The hull is divided into several watertight compartments, precisely to limit the entry of water in case of damage. This increases safety and maintains buoyancy even with part of the structure compromised. In addition, there are ballast tanks. They allow for adjusting the draft and balance of the ship during operation. By filling or emptying these tanks with seawater, the crew can correct for lateral tilt, compensate for load variations, and keep the ship within safe stability limits. Submarines use the exact same principle, but in an active way. They control their density to go up or down. In all cases, the principle is the same: to control the relationship between weight and volume displaced. And when a ship crosses the sea, it is not simply floating on the surface. It is partially submerged, balanced within a field of pressure. Water exerts force in all directions, but as pressure increases with depth, the lower part of the hull receives a greater force than the upper part. This difference creates the thrust that supports the entire structure. The ship descends only to the point where the weight of the displaced water equals its own weight. From then on, it remains in equilibrium. Ultimately, what keeps hundreds of thousands of tons above the ocean floor is not lightness, it's calculation. It is the precise control of average density, load distribution, and stability. As long as these three things are within the designed limits, the system works. If any of them fail, the balance is lost. A ship does not defy physics. It works precisely because it respects every detail of her. Thank you for watching until the end. Subscribe to the channel, leave a like, and turn on notifications because that really helps the video reach more people.